Hi, Mick McQuaid here with 782 Visual Analytics, and today is chapter 11 of the textbook. The textbook is R for Data Science. This is in part 2 of the textbook. The chapter is Strings and Regular Expressions. So you'll often have to deal with strings in your analytics, and you'll often use regular expressions to do so. And to do this, you're going to need an additional library, so that you'll have to load the base tidyverse package, all those libraries, and then you'll also have to load the library string R. Here are some examples of strings. So here I've assigned strings to variables. So P gets, this is a string, and then I've surrounded that with parentheses, and the parentheses simply cause the result of the assignment to be displayed on the screen. So it's equivalent to typing this followed by P followed by another pressing enter at the R console prompt. So it's this, it doesn't have a material effect, it's just a shorthand way of seeing what you've done. So in addition to this string, I have, so this strings are delimited by double quotes, or by single quotes for that matter, but that creates a problem if you want to have a double quote in a string. So there are several ways of doing that, and here are 3 of them. There's actually at least one more way. So you can surround the string with single quotes and put double quotes in it. You can escape the quotes with backslashes. You can escape the single quotes with backslashes. I could also have escaped the double quotes here with backslashes. Now to see the raw string itself, you won't see the raw string itself. You'll see the result of the assignment, but that's not the same thing as the raw string itself. You'll need to say write lines with the name of the string in order to see it, and you'll see that that these strings look a little bit different. And you can get help on character quoting by typing in question mark, single quote, double quote, single quote, or you can type question mark, double quote, single quote, double quote. Either one of those, and any other combinations R will not understand, because I've tried that. And there are 39 functions that start with STR_. Now there are also about 200 functions that start with STRI_. So the STR_ are kind of a beginner set or a basic set, and that's all that we're going to talk about. So a couple of the functions are str_length and str_c. str_length simply gives the length of a string. So here we have a string of length 1. That's this one right here. Here we have a string of length 18, that's this string here. And here we have a string of NA, and its length is NA. So we don't know what NA is, so we can't know how long it is. Okay, so we can combine strings with str_c. So we have 3 strings here, and combined, they are just x, y, z. Instead of just combining them, I could combine them with a separator in between. And here I've done that. So you can type in this comma, or for that matter a space, and put the strings in separated by whatever that separator is. Now if you combine strings with vectors of strings, it gets a little bit more interesting. So here I have a string, then I have a vector of strings, and then I have a string. So when I combine them, what I get is first this string with the first component of this vector and this string, then this string, the second component of the vector, and this string. So this is the output. This is the first string, the first component of the vector, and the third string, the first string, the second component of the vector, and the third string. That doesn't work for NA, out of the box anyway. So if I try to do the same thing with NA, see I've got this set up exactly the same way, and you can see that NA is not surrounded by the hyphen and the pipe character. However, I can explicitly request NA to be included by using the STR_replace_NA function, and that will make NA behave like a regular string. Otherwise, it will be silently passed over. Vectors of strings differ a little from strings, so we saw before that we could combine these three strings, but if we try to combine a vector of three strings, we get a string of vectors. And this is a little bit hard to understand. In fact, the documentation, I'm just going to read you from the documentation. It says, to understand how STR_C works, you need to imagine that you are building up a matrix of strings. Each input argument forms a column and is expanded to the length of the longest argument using the usual recycling rules. So this is a little bit potentially unexpected. You can get rid of that behavior by using collapse to convert to a single string, convert the vector of strings to a single string. Objects with length 0 are silently passed over. So this entire part here, if birthday and happy birthday, is going to get passed over because birthday is a Boolean that is assigned the value of false up here. So we're going to have the string good followed by a space, followed by the time of day, which is morning. So it'll say good space morning space name Hadley, and then comma. Oh no, there's no comma. And if, so that here's a whole if expression inside of the STR_C function. If this expression were to evaluate, if birthday were true, then the string would include and happy birthday, followed by a dot. But because this is false, it's as if this whole part here, the part that's highlighted in blue, doesn't exist. So this is the result that we get. We can extract part of a string with STR_sub, and if you're familiar with string processing in other languages, this may seem a little unusual in two respects. One is that we start counting with 1, so this is position 1. And the other one is that instead of starting with a position and continuing for a length, we start with a position and end with a position. So this is saying start at position 1 and end at position 3. So here's 1, 2, 3, so just take APP from this string, and that's the result here. 1, 2, 3, and just take BAN from this string. Take PEA from this string. And we can also count, so in addition to being positions 1, 2, and 3, this is position -5, -4, and -3. So we can start at position -3 and go to position -1, which is this position here, and get PLE, which is here. So you can think of this either as having the positions having the reverse names when they're negated, or you can just think of it as counting backwards. So -1, -2, -3. And we can assign values. So this portion here is just an expression that converts the first character of the string to lowercase, but it doesn't save it anywhere. Only with this assignment operator are we going to save it, and the location where we're going to save it is in the first position of the string. So this whole thing together modifies this string, and then if we display the string, we'll see that it's been modified. Strings depend on locales. So the examples that I'm going to use in this class are mostly US locales, so you may not notice this, but let's say that for your project you're using an international data set. You may be very surprised by some of the results that you'll get if you stay in the US locale. For example, Turkish has 2 I's, with and without a dot, and it has a different rule for capitalizing them. So if we capitalize these in the US locale, we get 2 identical characters. But if we set the locale to Turkey, we get 2 different characters. So keep that in mind if you're dealing with data sets, international data sets, and different character sets than the US examples from class. Okay, now the textbook has a section on regular expressions, and it uses a function called STR_view, and that requires you to install and load HTML widgets and its dependencies. And you can either do it through the graphical installer, or you can do it like this in the R shell. And then STR_view will show its output in the default browser. So here's an example. So this is a screenshot from my browser, and I don't like the way that it looks. So STR_view here puts a rectangle around the portion that's been matched. So the regular expression here is just a literal. It's just a string literal, AN. So it's simply looking for an occurrence of AN. If I said STR_view_all, it would match both of the ANs here. Now as I said, I don't like the way that this looks. So for the remainder of these slides, I'm going to simulate the behavior of STR_view, and here's an example of that by simply underlining the part that it would be highlighted. So you can imagine this, or if you run this yourself, you'll get a rectangle around the part that I've underlined. So in this example, using the same vector, I've used dot to match any character. So this is searching for a single character followed by A followed by a single character. So this matches. This does not match because it overlaps. So after this match has been consumed, the next string that the regular expression is looking for is this, and that does not match this. This, however, does. So it's important to remember that there's no overlapping. I think I'll mention that again in this lecture. And it's important to note that the regular expressions work from left to right, at least in English. I don't know if you do this, say, in Arabic, or some right to left language, if you'll get right to left regular expression matching. I'm just not familiar with that. Okay, now because you can use the dot to match any character, looking for an actual dot is a little bit complicated. So we have to use a backslash to look for an actual dot, and because the backslash is a special character, we have to use a backslash to escape that. So we need this cumbersome construction, double backslash dot, to look for an actual dot. So that finds the dot here and matches this string. We can use other meta characters, so the circumflex or caret matches the beginning of a string, and the $sign matches the end of a string. And that's pretty common. You'll see that in a lot of languages. So here the circumflex or caret is matching an A that occurs at the beginning of the string, so it only matches the A in apple and does not match any of the other A's. And similarly, if we put A followed by $sign, this is only going to match an A at the end of a string. So it's only going to match this A. And we can use both to match only a complete string. So if we put a caret and a $, around apple, and we have these three strings, only the one where apple is a complete match will be matched by this regular expression. That was unintentional, by the way. Character classes and alternatives. So we can, in addition to matching explicit characters, so string literals, we can match various character classes. So we can match digits, we can match white space, we can match alternatives. So these are these represent any single character, A, B, or C, not a combination of those characters. This represents, so previously we used the caret to refer to the beginning of a string. If the caret appears within brackets, it means not. So this means not A or B or C. So this matches any single character that's not A or B or C. And that would include numerals as well as letters. A or B here is means that we're matching A and B as strings. So A isn't just a single character here. I should have called this like string 1 and this string 2 or something like that. Here's an example. These two strings are gray and gray, and by matching either E or A, we're able to match both of them completely. Now, if we took away these parentheses, so imagine that we just had this expression without the parentheses, it would match the GRE here, and it would match the AY here, but not the rest of the expressions. So generally you have to use, usually if you use the OR bar, you're going to use parentheses to disambiguate. Okay, and we can do repetition with question mark, plus, asterisk, or curly braces. And these are numerals, so exactly 1, exactly 2, 1 or more, at most 2, 1 to 3, something like that. The question mark is a lazy operator. That means it will match as soon as it can. The plus and the asterisk are greedy operators. They'll match as much as they can. And you can influence the braces operators by putting question marks or pluses after them to make them greedy or lazy. So here's an example of the lazy question mark with the CC. So this matches a C followed by either 0 or 1C. So that matches here. You know, that's not that lazy because that really should match just 1C. Is that really lazy? 0 or 1C. That's interesting. So I've run all of these, so I know that this is actually how it works. But it's not as lazy as I would have thought. Okay, and then here's CC with a plus. So this is going to match as many C's as it can. So 3 C's. C followed by either L or X, and any numbers of L or X's. So we have a C followed by an L, so that matches. And then do we have another L or X? Yes, we have another X, and another X, and another X. It's going to keep matching until it gets to a token that's not an L or an X. C with the curly braces and a 2 is going to match exactly 2 C's. This is going to match 2 or more C's. This is going to match 2 or 3 C's. And here's why I would think that's the 2 C's followed by the question mark. So this definitely works this way. So the smallest match that legally fits this is 2 C's. So it matches 2 C's. Okay, so we can define groups, and we can then refer to those groups as \1, \2, and so on. So the first set of parentheses that we put in will be matched by \1. We can use this as many times as we want. And as many times as we use parentheses, we can add more numerals here. And when we use \1, we have to escape the backslash, so it's double \1. So there's a list of 80 fruits in the string R library. If you just type in fruit, you'll get 80 results. And some of these results have repeated pairs of letters. And that's what we're finding here. So this is any pair of letters, and this is that same pair of letters again. So and it's only these 6 fruits that match out of all 80 of them that have the repeated pairs of letters. And some of them I didn't even know were fruits. Okay, there are many things we can do with regular expressions. We can determine which strings match a pattern. We can find the position of matches. We can extract the content of matches. We can replace matches with new values. We can split a string based on a match. So you can detect matches. So here you're going to detect whether or not there's an E in any of these vectors. So is there an E here? True. Is there an E here? False. Is there an E here? True. So the vector X, the regular expression E, and the output is Boolean. The output of STR_detect is Boolean. Now we can use the fact that a Boolean true is equal to 1 and false is equal to 0. So there are 65 words that begin with the letter T in the words list. So there's a list of about 980 common words in the string_R package. And in that list, 65 of them start with the letter T. Each time that STRDetect finds one of them, it returns true. So it returns true 65 times. That 65 is equivalent to 65 ones. So by wrapping this in the sum function, we can get the sum of those 65 ones. We can also get the average of those 65 ones. We can see, what the average number of words that start with T is. And here we're finding that 27% end with a vowel, although Y is conspicuously absent from this list of vowels. So we can find all the words that contain at least one vowel and negate them to find words without vowels. Now I should point out, I was a little skeptical about whether there are words without vowels. The words, so notice that they define vowels without Y. So words like fry and sky are defined as having no vowels. And that's all the words except one are words that end in 3-letter words that end in Y. And the one that's not, and by also. So the one that's the other one that's not is Mrs. MRS, which I would not consider a word, but it is in this list of 980 common words. So we can find all the ones with vowels and negate that, and that's going to give us the number of words with, it's going to give us a vector of falses and trues, where the trues match the words that have no vowels. We can also find the words that consist only of consonants and make a vector of trues and falses out of that. And then we can compare them, and we find that when we compare them that they're identical. Now this expression is a little bit more complicated than the expression above. So this expression is saying the beginning of the word followed by not, this is, not any vowel. The plus means followed, so any string of characters that are not a vowel up to the end of the word. So you may find this a little bit cumbersome to use. You may find this expression a little bit cumbersome to use. However, it is more robust than this method, and I'll show you why. So the previous example, the first example was more understandable, but if we try to use it with STR_subset, this works. This actually gives the list of common words that have no vowels. This doesn't return a vector of Booleans. This actually returns a vector of those words. This, on the other hand, fails. So this is the same, using the same logic that we used with STR_detect. This isn't going to work, though. So let me return to this for a second. So my point is simply that although this language is more cumbersome, this regular expression is more cumbersome, it works in more settings than the other one. STR_subset is a wrapper around logical subsetting. So these two expressions are equivalent. So this is a logical subsetting, and this is a logical subsetting. So this is finding all words, the subset of words that end in X in the words list. So that these are the only 4 words that end in X in the list of common words. Now, if we're going to place the strings into a data frame, or in particular a tibble, we're going to use filter with STR_detect. So here we're going to detect the words sequence along word. Let's see. So this is I'm completely forgetting what this is. Filter P. So P, string detect all the words that end in X. Oh, this is the sequence along word is its position in the vector of words. So this is the position of box. So there's a list, as I said, of 980 words. This is in the 108th position. This is in the 747th position, and so on. STR_count gives the number of matches per string. So this is telling us how many times the letter A occurs in apple. And I have to remind you that this is non-overlapping. So if this were a more complicated expression, for example, if it were ANA, it would have a count of 1 for this word. And we can use other functions, other arithmetic functions on STR_count too. We can find out how many vowels there are on average per word this way. Okay, so we can use this with mutate. So this is the P that we used 2 slides, that we created this 2 slides ago out of the words list. And by counting the number of vowels in word, we get this number in this column. And then by counting the number of consonants in the word, that is not A, E, I, O, U, we get the number in this column. So this returns a tibble of 980 rows, because there are 980 of these common words, times 4 columns. We already created this column I a couple of slides ago. As I mentioned before, matches never overlap. So ABA occurs here and here. It occurs twice, the count of it. And if we do STR_view without the underscore all, we would just get this match here. If we say it with the all, then we get both matches. Now there's a list of sentences called the Harvard sentences that's built into the string R package. There are 720 of these sentences, and here are the first 6 of those sentences. So the next series of examples is going to use these sentences. So let's make a regular expression from a list of colors. So here's a list of colors, and it's in this vector, colors. Then we use STR_C, and if you recall, the behavior with the vector is a little bit different. So we're going to collapse it and use this as the separator character. So the result is color match now looks like this. And we could have created color match like this previously. There actually is a list of colors, I think. Let me just check this. Colors. Oh, no, I'm wrong. There's not a list of colors. Okay, so we had to create a list of colors. So one way was to create it like this. Another way would have been to just create this directly. Now, we could, so the textbook doesn't do this. I'm just adding this in, throwing this in, because there's an odd thing in the textbook. The textbook finds, the textbook is going to look for these colors, and red is also going to be part of some other words like colored or ordered or something like that. RED is going to be part of those other words. So what we could do is, oops, here it is. What we could do is make them whole word matches. So this means the boundary of a word. This \B means boundary of a word, and we have to use the double backslash because the backslash is a special character. So we could do it this way instead, and this way actually will work better. And I think I did it this way in the later slides. I can't remember now, but I think I did it this way. Okay, so here's the next thing that we do. We take sentences and color words and STR_subset. So this is going to give us the sentences that have colors, and this is going to just extract the colors from them. So these are the colors that actually appear, or this is at least the head of the sentence, the actual string matches. So these are the first few colors that appear. And if we do a count of these sentences and put it in, oh no, we're not doing a count of them. This is a subsetting vector. This part right here is a subsetting vector. So this is sentences that have a count of more than one, of greater than one color word in them. So here's, there are only two such sentences that have two color words in them, blue or red ink and tinged with orange red. There's a section now in the textbook where they try to find subjects of sentences, and I sort of take exception to that. If you want to do natural language processing, R is not the right tool for the job. There's a very popular library in Python called Spacy that's currently the fashionable way to do natural language processing. If you have natural language processing to do, don't try to do it this way. This illustrates some facts about regular expression processing, but it is completely ridiculous as a method of natural language processing. So we're going to do it, but take it with a grain of salt, okay? So articles plus are going to be any occurrence of either a or the. These are the only two articles we're going to consider. There are other articles, obviously. We're just going to consider these. And any string that does not have spaces in it. So that's any word. So this section right here refers to any word. And notice that we're grouping this. So we can refer to this as \1, and we could refer to this as \2. Okay, and then we're taking the sentences, the list of the 720 sentences, and we're getting the subset that have this. And then we're taking the head of that, and then we're putting it into has art plus, and then we're string extracting the article plus from this. So we get the smooth, and you can see right away that this is not finding the subjects of sentences, it's finding an article followed by either an adjective or sometimes a noun or sometimes something completely else. I forget what this was. But it could be almost any part of speech. Okay, then we can use STR_replace to replace matches with new strings. So in the very simple case here, we're replacing any occurrence of a vowel with a dash. And notice that it just replaces the first occurrence. This is very typical of regular expression processing, that you use a separate function. So this STR_replace all is a separate function that would replace all of the occurrences. So you might want to just replace the first occurrence, or you might want to replace all of them, but it's typical to have two separate functions to do that. And we can use a named vector to do this. Now, in this particular case, the order of these doesn't matter. So one house appears to be paired with 1 equals 1, but this vector could be ordered differently. It could be 3 people, 2 cars, and 1 house, or any other combination, and this could be any combination. It would still recognize is this exactly the same way and would replace each occurrence of 1, of the numeral 1, with the word 1, each occurrence of the numeral 2 with the word 2, and each occurrence of the numeral 3 with the word 3. Here's a really good example of the use of the grouping parentheses. So we can insert components of a match. So this, we saw this previously, this refers to a word. This is a series of things that are not spaces, as many as you can find of things that are not spaces. So birch, for example, would fit this. Slid would fit this. In other words, all of these words would fit this. So this is a way of referring to a word. And this is the first one, so it can be referred to as \1. And what we're replacing is we're replacing \1 with \1. We're replacing \2 with \3, and we're replacing \3 with \2. So instead of the birch canoe slid on the smooth planks, the canoe birch, blue sheet the. So what we're doing is changing the second and third words in each sentence. We're swapping the second and third words in each sentence. And this is a toy example, but it's an example of a very powerful feature of regular expressions. You can do a lot with this feature of regular expressions. Okay, and then we can also use STR_split to split a string into pieces. So we're splitting it here on spaces. So it's splitting the sentences into words. And we can also do this into a matrix. So if we say simplify equals true with the string split, it'll return a matrix. And some of the cells of the matrix may be empty because not all sentences have the same length. So these two sentences happen to have the same length. I think the matrix that you'll get will have the number of columns of the longest sentence that you have. And it just happens in this case that these two sentences are both each 8 words long. So the matrix is 8 columns long. We're seeing the first 6 columns here. We would see column 7 and 8 here if I had enough room on the screen. I guess I could have used a smaller typeface, but instead we're seeing column 7 and 8 on separate rows. This is just an artifact of trying to have a reasonable size typeface on a small screen. Okay, and then last and not necessarily the most important, we can, in addition to simplify equals true, we could also say n equals 2 or n equals some number, and then we split only that many times. So we split off the first word in this case, and then return the rest as the second column of the matrix. Okay, and that's it. I've just hit on a few of the high points of this chapter. There's plenty more detail for you to investigate. You should become comfortable with the use of regular expressions in multiple languages. Now, personally, I prefer to use regular expressions in an editor called Vim for short files, and then export them to R or whatever I'm working with. Or if I have large files, I use Perl for convenience. Perl is very convenient for processing strings and regular expressions. And in fact, actually most languages, most contemporary languages, have their regular expression processing based on Perl's regular expression syntax. But the most fashionable, definitely right now, language for dealing with regular expressions is Python. So it has a very nice looking syntax, and so it's very popular for that. R, I think, is more known for its graphics and its large selection of data analysis packages. But knowing how to use regular expressions during data analysis in R can shortcut many tasks. So please do pay close attention to it. And thank you for your attention.